The most common random experiment involves tossing a coin, and the next common is rolling a die. Now if I toss a coin n times and the probability of head of the coin is p, and I count the number of heads, then we know that this random variable number of heads has a distribution which is called binomial with parameters n and p. Now if we do the same thing for the die, so we roll the die n times and the probabilities of the 6 faces are p1 to p6, of course they add up to 1. In that case, I may count, just as in this case I counted the number of heads, which automatically also gave me the number of tails. In this case, I will count the number of times each of the faces occur. So number of times 1 occurs up to number of times 6 occurs. The total will always be equal to n. In that case, this random vector will have a distribution that we shall call multinomial, just as this is binomial, parameters n and p1 to p6. Now you understand there is a little redundancy in both these things. I could as well just work with 1 up to 5 because the number of times 6 occurs could be obtained by n minus those things. Similarly, I really do not need to specify all the 6, even if I drop the last one, because they add up to 1, you can work that out. But in case of multinomial, we prefer to use this particular notation. So according to this notation, this is also a multinomial. You have to count both heads and tails separately. Then it is a multinomial n, probability of head and probability of tail. But in case of binomial, we just drop one of them and write it as only a real valued random variable. Now there is nothing special about a 6-faced die. We consider this as it is something like a 2-faced die. In general, it could be any k-faced die, and then the probabilities will be p1 to pk. They must form a probability vector, non-negative, they must add up to 1, and these things should add up to n. They are all non-negative integers. Now based on this description, let us try to work out its probability mass function. So here is our setup. We have a random experiment with possible outcomes 1 to k. They have probabilities p1 to pk. They add up to 1. I repeat this experiment randomly n times, like rolling the same die n times. And I count the number of times I get 1, number of times I get k, and call them x1 to xk. My question is, given some values, little x1 to little xk, what is the probability that x1 equals x1, xk equals xk? Now one thing is obvious, that all these little xi's, they should be non-negative integers because we are counting things, and also they must add up to this little n because in every trial one of them has occurred. To understand how we compute this, let us take a simple example. I have taken k equal to 3 and I have got this outcome. So what is n? 1, 2, 3, 4, 5, 6, 7. So n is 7. I have run this experiment 7 times. In my first run I got 2, second run I again got 2, then I got 3, 1, 1, 1, then I got 3. So in this case my x1 is 3, x2 is 2, and x3 is again 2 because I have got exactly 2 3s. Now what is the probability of this particular outcome? I have got 2 here, I have got 2 again, so it is p2 squared. I have got p1 3 times, so I have a p1 cube, and I have got 3 twice, so p3 squared. So if I get this particular outcome, that will be the probability. But no one told me that I got them in this particular order. All that I know that there are 3 1s, there are 2 2s, and there are 2 3s. So it could very well be that this one was a 3 and this was 1. That is also have the same probability. So how many possible such things are there? That is pretty easy, because I can see that there are 7 symbols. So 7 factorial, out of them 3 are identical, 3 factorial, 2 are identical, another 2 factorial, these 2 are also identical, another 2 factorial. So this is the total number of ways I can have 2 2s, 2 3s and 3 1s. For all these cases, the probability is the same. So the total probability is this times this. So once you understand this argument, we can do it in general to get the answer. N factorial divided by x1 factorial times etc. up to xk factorial. Then p1 to the power x1 etc. product pk to the power xk, and all these things when for all I, xi's take value 0, 1, 2 etc. non-negative integers, and the total must be equal to n. If this condition is not satisfied, then of course that's an impossible case. So it is 0 else. That is the PMF of multinomial distribution with parameters n and p1 to pk. So we have seen that there are 2 ways of defining the multinomial distribution. First, as just by rolling die, so in terms of the random experiment, and then we actually could define it using the PMF, which looks somewhat complicated. In most cases, you will find that the random experiment definition is easier to work with. So here is a theorem that you can prove very easily using that definition. So I give you x1 to xk, that random vector has multinomial distribution with parameters m and some p1 to pk, and y1 to yk, same k, that is also multinomial n, which may be different from m, but the same set of probabilities p1 to pk, and they are independent. In that case, if you add these 2 random vectors, because they are of same length, you can add them, x1 plus y1, x2 plus y2, all the way up to xk plus yk. That would again be multinomial with these 2 parameters adding up, m plus n. These were same and they will continue to remain as before, p1 to pk. Now of course you can try to prove this directly using the PMFs. That would be a pretty nasty business, lots of sums, etc. But this is just trivial when you think of it in terms of the random experiment definition, because this one says that you have a k-faced die with probabilities p1 to pk and you have rolled it m times. Now, since the pi's remain the same, so basically you are taking that same die once again and rolling it for n more times. And thanks to this independence, the first set of rolling has nothing to do with the second set of rolling. So all in all, you have got m plus n rollings of that same die. Then what is this x1 plus y1? It measures how many times you have got the outcome 1. x1 gives you how many times you got it out of the first n rolls. y1 gives you how many times you got it out of the next n rolls. So x1 plus y1 gives you the total number of times 1 occurred out of these m plus n many rolls. Similarly for all the other things, so directly from the definition it has to be the total number of rolls m plus n, and it is the same die, so I just copy it over here, and that is multinomial. So that is a very useful theorem. We have already seen a similar theorem in case of binomial, and that is natural because binomial is a special case of the multinomial distribution.